finding the antiderivative is going to work out the same as it did previously. We will say let u equal 1 plus 2x cubed. That's a good choice. Let's make that a little clearer. Okay, then du equals 6x squared dx. That's sort of close. We actually want just an x squared. So let's say 1/6 du, or 1/6 du equals x squared dx. Alright, also, I'm going to go ahead and write it out this way. Okay, our a equals 0, and actually let's just draw a chart. I'm not going to explain this one. Let's go from our x values, our limits a and b. We want to find out what those values are under u. So my endpoints were 0 and 1. If I evaluate those into my u function here, if I plug in 1 here, I get 3. So my new endpoint is going to be 3, my upper endpoint, my upper limit of integration. If I evaluate this at 0, I get 1. So what I'm going to do is have an integral from 1 to 3 of 1/6, I'll put that in there, 1/6 du, and that is u to the 5th. One benefit to changing the limits is that I actually don't have to go back in terms of x. I can deal completely in u now. So this would be u to the 6th over 6, evaluated from 1 to 3, and I'll keep my 1/6 in there. And that should be 182 over 9. I can just evaluate those two endpoints, and I'm done. I don't have to go back in terms of x because I changed those limits from limits in x to limits in u. All right, example 6. Evaluate this integral. All right, well, it looks like our composed function here is 4x squared plus 3. That means our du is 8x dx. However, we want to substitute in an x dx, so we'll modify this by a factor of 8. 1/8 du equals x dx. Okay, and I've got my x endpoints, and I want to convert those to u. So those are 0 to 1. Evaluating that in there, I get 7. And evaluating at 0, I get 3. So I'm going to take the integral from 3 to 7 of 1/8. I'll go ahead and factor that out. Du, and that is e to the u. Alright, well, that will be e to the u. It's the only function that is its own antiderivative. Alright, so this will be 1/8 of e to the 7 minus e to the 3rd. Just go ahead and leave it like that. And that will be approximately 134.568. Let's go ahead and box all of that in. Alright, one last example with this. This one has a small trick that turns out to be very handy later on in calculus. Evaluate the integral from 0 to pi over 2 of cosine squared theta d theta. Alright, there is a trig identity, and this is what comes in handy. Cosine squared theta equals 1 over, okay, so this is going to be 1 plus cosine of 2 theta over 2, which is equal to 1/2 plus 1/2 cosine 2 theta. So what this becomes is the integral from 0 to pi over 2 of 1/2 plus 1/2 cosine 2 theta d theta. Let's put this in brackets. Okay. Okay, well, the first part, I'm going to treat this as two integrals, actually. I'm going to break this up because I can do that. Plus 1/2, integral from 0 to pi over 2, cosine 2 theta d theta. For the first one, it's going to be fairly straightforward. That's going to be 1/2 theta, evaluated from 0 to pi over 2, which will be pi over 4. Alright, so the first bit is pretty straightforward. For the second, we want to let u equal 2 theta, which means du is 2 d theta, or 1/2 du equals d theta. So this actually gets a u substitution. We get a u substitution there. So this is going to be the integral. I'll leave the 1/2 constant there. Cosine u du. Now my limits are going to go from 0, and these are thetas, to my u values, from 0 to pi over 2. Okay, evaluating that into 2 theta, okay, that is going to be pi and 0. So the integral from 0 to pi of cosine u. And notice we had to put in a 1/2, so actually there should be another 1/2 coefficient there. So this is 1/4, and this is sine u evaluated 0 to pi. Well, at 0 and pi, sine is 0. So this is pi over 4 plus 0, which is just pi over 4.